All right, so for part two, we were picking up on the torque on a flagpole. And I haven't really left myself enough room for this one. Oops. But I'm going to start by sketching out this scenario. So I have a 3.2 kilogram flagpole extending from a wall at an angle of 25 degrees from the horizontal. So let me start by drawing that. Out here, I have my pivot point. Here's my wall. And then my flagpole is coming out like this. And I know that this angle from the horizontal right there is 25 degrees. So I'm going to zoom in on this. There we go. And the total, let's see, where is it? The center of gravity is 1.6 meters from the point. All right, so here's my center of gravity right there. And that is at 1.6 meters. And then I know that the mass is 3.2 kilograms, and it's centered right around that point. So I'm going to start by drawing in my force here, which is my weight. So I'm going to take my weight, and it's going to go directly straight down like that. And I know that my weight is equal to the mass times the gravity, and I could also just call that the force due to gravity. Either one is fine. So mass times gravity is going to be 3.2 kilograms times 9.8 meters per second squared for a total weight or force of gravity of 31.36 newtons. Okay, so that's my piece. And then my radius, I could go with my 1.6 meter radius, but I need to in some way get a perpendicular line. And in this case, since I have the 25-degree angle right here, I think it would be easiest for me to find my radius perpendicular, that line right there, right? Because this would be my perpendicular radius to my force due to gravity. And that'd be an easy one because I know that this length, the hypotenuse there, is 1.6 meters. I've got 25 degrees. The perpendicular line would be, let's see, that is the adjacent side. So that would be R perpendicular equals 1.6 meters times sine of 25, right? Because it has to be the let's see, sine is opposite. Oh no, there's my problem. Sine is opposite over hypotenuse. I need to do cosine. So I was defaulting, but I'm going to shift to cosine of 25. So the cosine of 25, because it's a adjacent angle. So I got to really pay attention to those angles and figure out which is the right trigonometric function. Sine, remember, is opposite, so that would have given me the vertical component, which I don't want. I want the horizontal component because that's what's perpendicular to the weight. All right, so let's see, 1.6 times the cosine of 25 gives me 1.45. 1.45 meters. Okay, then I'm asking for the gravitational torque about the point of attachment. And I know that torque is equal to the force times the perpendicular radius. And in this case, I'm going to use the gravitational force. So that was 31.36 newtons times 1.45 meters for a grand total of 45.47, but it's only given to 2 digits. So that would be 45 Newton meters. So that would be my rotational torque, my gravitational torque around that point on the flagpole, which is helpful to know if we were engineering it, because that means that I need that much strength on the wall, right? So my little flagpole holder thing, the bolts or the screws holding it, got to be able to withstand that much rotational torque. Nice. Okay. So when I'm finding the center of gravity of a shape that's a little bit irregular, there's a few things that I can do. First, I could say I've got two masses. So we're changing gears just a touch. I've got two masses. I got a mass here and a mass here. Mass 1 is obviously larger than mass 2. Well, shouldn't say obviously, assuming that they have similar densities. Mass 1 will be larger than mass 2. Oh, no, it is obvious because the weight 1 is a bigger arrow. There you go. So the weight 1 is a bigger arrow. Weight 2 is a smaller arrow. So mass 1 is larger. And then in order to find my center of mass, which would be the same as the pivot point around which it would balance. So to kind of demonstrate that, I have a pen here. If I hold it precisely at the center of mass, if I can get it right. No, there. It balances perfectly. And in this case, I'm a little bit closer to the tip of the pen than I am to the cap of the pen because the cap is empty. The tip has like the ink and the grip on it. So my finger's a little bit closer to the tip over here. The center of mass is a little bit forwards, right? But it balances perfectly if I put my finger on that center of mass point. Okay. So I know that I can modify my radius to match the radius for the other one. So basically what I've got is I've got the weight, or weight times radius, but weight is a force, right? So this would actually be force times radius, and make them equal to each other, right? They should balance. And the radius is a distance, so I could use x if I wanted to do that. Force times radius is another way of saying torque, and torque is work in a circle. So I could also just set the energy on both sides equal to each other. I could think of this as setting work on the first side equal to work on the second side, or the torque on the first side equal to the torque on the second side, or the force on the first side times the distance of the first side equals the force times the distance on the other one. And obviously these would be perpendicular forces, and that would be around that equals point is the center of mass, or the pivot point. All right, now another way is you could do some fancy math. You could say, okay, I know that this force is actually equal to the mass times the gravity, so that would give me mgr on this side equals mgr on that side. Gravity is always the same, so boom, boom, do some math, and you could find that the center of gravity point, right, x of the center of gravity, is equal to x1 mass 1 plus x2 mass 2 over mass 1 plus mass 2. So that's another helpful equation. Or you could just set the two equal to each other and go from there. All right, let's go back up to the top and do a little example. All right, where should the dumbbell be lifted? I've got a 1 meter long dumbbell that has a 10 kilogram mass on the left and a 5 kilogram mass on the right. So step number 1 is we need to go to the coach or PE teacher in charge and ask people to please re-rack their weights more responsibly. We should not have a dumbbell that is that out of whack. Really poorly designed. Come on, guys. Then I could find the position of the center of gravity, the point where the dumbbell should be lifted in order to remain balanced. So this is assuming that the rod itself has no mass, which is okay. We'll just pretend. So finding the center of gravity of that barbell, I need to figure out, so that my first piece is that this is 2 times bigger, and this is 1 times, right? 10 is twice that. So my first part is this, in terms of radius, should be the opposite, because mx on this side should be equal to mx on this side. Since the mass is twice as big here, this should be half as big, or this should be twice as big, and this should be 1 times as big, right, in terms of the x's. So if I need 1 part here and 2 parts here, that's 3 parts total. So that'd be 1 part out of 3, 2 parts out of 3, and then it'd be 1/3 of a meter and 2/3 of a meter. So that would be the way that I first logic it out, right? I know that I've got 1 part to 2 parts because this is 2 parts mass to 1 part mass there. Just do the inverse, and this would be 1/3 of a meter to 2/3 of a meter. I could also use the equation, and the equation was x1 m1 plus x2 m2, x1 m1 plus x2 m2, all of it over the total of m1 plus m2. All right, so x1 in this case is 0 meters, right? I'm setting that as my starting point. So that's going to turn into 0 plus x2 is 1 meter times 5 kilograms over the two masses together, which is 15 kilograms, giving me a total of 5 out of 15. Kilograms cancels, leaving me with meters, or 1/3 of a meter, 0.33 meters, which is exactly where I thought it would be. So you could do either way, just kind of think through which one makes sense to you. All right, so let's stop and think for another one. These balls are connected by very lightweight rods pivoted at the point indicated by a dot. The rod lengths are all equal except for A, which is twice as long. Okay, that looks about right. Rank in order from least to greatest the magnitudes of the net gravitational torques around the pivots for arrangements A to D. Okay, so I'm going to draw this out. So in this case, I'm going to say that each line, right, is 1 radius or 1x. So here I have a mass down, so that'd give me a force of 1, right, a weight force of 1 times the radius of 1. And then 2m means I would have 2 of the forces there times the radius of 1. So that gives me a net of 1 unit of torque, right? My torque there would be 1, right? 1 radius times 1 force, because 2 forces times 1 minus 1 force times 1 leaves me with 1 times 1. 2 minus 1 is 1. All right, in this case, I have 2 mass right on the pivot point. Those don't do anything, right? They're right on the pivot, so they don't exert any torque. I only care about the torque part. So what I'm left with is the mass times the radius, which would be a net unit of 1 torque. 1 mass times 1 radius gives me 1 torque. And I'm just not really using units here, but proportions. This one, this mass doesn't do anything because it's on the pivot point, but I have 2m here, so that would be 2 forces, which gives me 2 torque, right? Because it has a radius of 1 and 2 forces, so 2 torque magnitude. And then here, I have a mass all the way out. I'm going to use blue for this one. That would give me 1 torque. And then this one is halfway out, so it'd be a mass times half of the radius. So that would give me half of the torque, 1/2 of the torque. So that total would be 1.5 torque. All right, so I'm supposed to put them from least to greatest. So that would be A, which is equal to C. Those two both have 1 torque, and those are both less than D, which is 1.5 torque, which is less than B, which has the greatest one, 2 torque. Okay. So we've started talking about torque. Now we can start talking a little bit about acceleration and tangential acceleration. So we could take a look here at this diagram and see that I have multiple forces. I have a pivot point, and around that pivot point, I've got a tension force. So we're imagining that this is maybe a particle swinging around in a circle on a string. The tension is due to the string itself, or the rod tension. And it's a force towards the center because of centripetal acceleration, A sub c. Then I also have a force going sideways. So that means I'm going to get acceleration around the circle, not just directional change, but actual like speeding up as I'm going around the turn. And so I've got tangential acceleration as well. All right. So for something like this, I could say that torque causes angular acceleration, right? The force that I'm putting on there, the force that I'm putting right here, right? That force is causing this acceleration, F equals ma. Or in this case, because it's angular, it would be A equals F over m. And when I convert it to angular, the angular component, the A turns into an alpha, the force turns into a torque, and the m I'm going to represent with an I. So this is actually like alpha equals the torque over the moment of inertia, I. But then I know that the moment of inertia is equal to mr squared, right? So the moment of inertia for a particle is mr squared. So I've substituted that in here. So that is the equation that I could use there. And I know that the torque is causing that angular acceleration. Pushing on it at the outside angle causes it to accelerate angularly. All right. So that brings up this moment of inertia issue. The moment of inertia is equivalent to the mass of the object. Now, it's not equal to the mass of the object, but it holds that placeholder. Basically, it's a sum of the mass times the radius squared. And that's why when I put in the I at the beginning, it didn't make any sense, because what I'm really looking at is the mass of this object times this radius of the object squared, right? Because acceleration, this might look familiar, was equal to v, it doesn't matter. That's the equation you end up with. All right. So I know that I is the moment of inertia, and that's going to be equivalent to the mass times the radius squared, or the sum of all the masses of the particles times the radius squared. The unit there would be kilograms meters squared. Or I could simplify it down and say that the angular acceleration is equal to the net torque over I, the moment of inertia. So moment of inertia is I. And as we mentioned before, this is equivalent to A equals F over m, or F equals ma, Newton's second law. This would be called Newton's second law of rotational inertia. So it's the rotational equivalent of mass. All right, and if, actually, yeah. So the moment of inertia depends on both the mass and how we distribute the mass. So if I have a whole bunch of mass, but I push it all to the center, then there's not very much radius. And since it's mass times radius squared, where it's located, how far from the center, really matters. So it's the total amount of mass and then the radius of that mass squared. So if I put the mass further out, I have a greater moment of inertia. So if the mass is concentrated around the rim like this, I've got a person here, a person here, a person here, then there's a larger moment of inertia. That means it's harder to get it rotating. If the mass is all close to the center, where all three people are huddled around the middle, then it's much easier to get going because it has a smaller moment of inertia. Now, this is also true for the opposite. It also means if the mass is around the outside, once it's going, it's harder to stop. If the mass is around the inside, once it's going, it's easier to stop. So things that have all their mass on the outside are hard to get going, but once they're going, they keep going, right? They have more inertia, so they keep moving. Things where the mass is closer to the center, it's easy to get them going, but then they also are easier to stop. Okay, so this would be like mass in the center, like a solid ball, versus a hollow ball where the mass is on the outside. Hollow balls are harder to start spinning, but easier, harder to start spinning and harder to stop spinning. There we go. Okay. All right, so this is a diagram. It's table 7.1, and we'll reference it quite a lot. This is just a whole bunch of equations of different equations for specific shapes for their moment of inertia. Ones that we will be using a lot. A cylinder or disc about the center is 1/2 mr squared. That's a helpful one. Cylindrical hoop or a ring is just mr squared because that's like a particle on the outside edge. You might use this guy, a thin rod about the center. Anyway, depending on what shape they explain for you, it would be using one of these equations for it, right? A solid sphere is 2/5 mr squared. So that's just how you can kind of figure out what is the moment of inertia if you know information about their overall mass and their radius, and they have a consistent density. All right. So let's do another stop and think. I have 4 very lightweight discs of equal radii. Each have 3 identical heavy marbles glued to them as shown. Rank in order from largest to smallest the moments of inertia of the discs about the indicated axis. Okay, so here's the axis, and this is a radius of 1, 1, 1. So it is mr squared. So this is the mass time, I'm going to call this a radius of 1, radius of 1, radius of 1. So this would be the mass times radius 1 squared, mass times radius 1 squared, mass times radius 1 squared. I'm going to say this is 3, right? Because each one is a mass of 1, radius of 1 squared, which is 1, so that's 1. This one, mass is 3, but the radius is like 0. It's not actually 0, but I'm going to say it's about 0, right? So that's pretty much nothing. This one, I have 1 in the center. That's really 0 because it's, stuck there. Then this one is big. This one is big. So that's a radius of 1, radius of 1. So that has a total of 2, right, for the moment of inertia. And then this one is interesting, right? This one has a radius of 1 there. So that'd be 1. And then this one has a radius of 2r, right? So that'd be mass times 2 squared. 2 squared is 4. So that would be 4m, or 4 plus 1, which gives me a total of 5. So that's our winner. It's got one way the heck out here, and that one is doing some work. This whole disk would be spinning around like that, right? Doing a big loop, not spinning around the center point. So largest to smallest, the moments of inertia. That would be D is the biggest, which is going to be bigger than, the next one is A, which is going to be bigger than C, which is finally going to be bigger than B. All right. So let's start an airplane engine. Oh, like old school, one of those prop engines where you do the like vroom, vroom, vroom. Okay, so that is using torque, right? It's spinning this guy around its axis. The engine in a small airplane is specified to have a torque of 500 Newton meters. This engine drives a 2-meter long, 40-kilogram single blade propeller. 2-meter long total. Okay, so that means the radius is 1 meter, right? And the total length is 2 meters. 40 kilograms. On startup, how long does it take the propeller to reach 2,000 RPMs? Okay. So it has a torque here, and I know that, wrong way, torque is equal to the mass, which is inertia, times the angular acceleration, right? Or the angular acceleration is equal to the torque over the moment of inertia, and the torque over the moment of inertia. So now I got to figure out the moment of inertia for this thing, and it looks like it's a straight line stuck in the middle. So I'm going to check back against my previous diagram. Straight line through the middle, 1/12 ml squared. So I'm going to do 1/12 ml squared as my diagram. All right, so this is going to be 1/12 ml squared because it's like a rod stuck through the middle. The angular acceleration is equal to the torque was 500 Newton meters over the inertia, which is 1/12. The mass was 40 kilograms and the length was 2 meters squared. Okay, and that will give me an angular acceleration of 2 squared is 4. 4 times 40 is 160, divided by 12 is 13.33. 500 divided by that is 37.5. 37.5 radians per second squared. Okay, so now I know how fast it's accelerating. I need to get it up to 2000 RPMs. So 2000 RPM, since I have this answer in radians per second squared, I'm going to convert 2000 RPMs into radians per second. So 2000 RPM, that's revolutions per minute. And then a minute has 60 seconds. That'll cancel my minutes. And then I've got revolutions, and I need to get rid of revolutions and say there are 2 pi radians in one spin, one revolution. So it's going to be 2000 times 2 pi divided by 60. 2000 times 2 pi divided by 60, 209.4. Okay, so 209.4 radians per second is what I need to get up to. I have an acceleration. This is a speed. And I need how long? I need a time. So I know that acceleration is equal to the change of velocity over the change of time, right? So 37.5 radians per second squared equals my change of velocity as I need to go from 0 up to that value, 209.4 radians per second over the time, multiply time over, divide that over. So it's going to be 209.4 divided by 37.5, giving me 5.6 seconds. So time equals 5.6 seconds to get the engine going to its maximum speed of 2000 revolutions per minute. That seems reasonable, right? 5.6 seconds. Vroom. Yeah, that checks out. Cool. All right, so that seems to work. And I wrote that very small. Okay. So other stuff that is helpful to know. We've already mentioned that we can use the radius. So we can also do a comparison between the linear velocity and the angular velocity, where the angular velocity times the radius gives me the linear velocity, or the angular acceleration times the radius gives me the linear acceleration. One other thing to note is that energy and force, but energy especially, is split between rotational and linear or translational for rolling objects. So if I have two options, either a rolling object or a sliding object, assuming no friction on the sliding object, the rolling object is going to go slower than the sliding object. So if I race like a ball versus a car down a ramp, in fact, I think I have a car and a ball, and I could race them down a ramp, and I'll do that in just a second. The car should win because it's sliding. I mean, the wheels are rolling, but the wheels have such little mass, they have almost no moment of inertia. Whereas the solid ball, or the hollow ball especially, takes a while to get going, right? It has a larger moment of inertia. because it's using some of its potential energy for rotational kinetic energy instead of just translational kinetic energy. All right, so a last one, a wheel rolls without slipping. Which is the correct velocity vector for point P on the wheel? So point P is right here. All right, so I would say it has two things going for it. It has its translational velocity, and it has its rotational velocity. So its translational velocity is shown right here with V. So that would be that. That would be translational. And then it's also going up, like tangentially on this here, on this object. The circle is going like this, right? Like that. And so tangentially, it's going up right then. Probably not as fast as it's going sideways. So this should be a smaller arrow, more like that. But you get the idea. I'll kind of erase that bit if I can. I cannot. That's fine. Oh no! Overdid it. Tried to do too much by erasing, and now I've erased everything except for that circle. Come on back, iPad. There it is. Okay, so I lost my blue line, which is perfect because I was trying to erase it. So I said that we had a translational velocity vector there. We had a vertical velocity vector like there, a little bit smaller. So then overall, that would leave me with its total velocity kind of going like that. And that one would be C, right? C has that direction. It's going sideways, but point P is also going up because it's moving to the top of the circle. So overall, it's going that way. All right. Last piece is I am going to stop screen sharing so I can show you what happens when we race a car and a ball. So let's see what I can do here. I've got a trash bin. Not sure if we can make this work, but we'll try. All right, so this is one of these brilliant when your classroom has been moved and we're teaching remotely. Okay, so I've got a car, if we can see it. I have a ball over here. So if I set them both up next to each other, and I'll run two cars just in case you can't see the first one. There we go. So the cars should just about always win because they aren't doing as much rotational kinetic energy. 3, 2, 1, go. They do. The cars went off first. Hopefully that was visible on screen. So some of that like kinetic energy in the ball was going to rotational kinetic energy and not to translational forwards kinetic energy. And with that, we are going to stop and hit some practice problems for Chapter 7, rotational energy. Good job.